Hello and welcome to homework 2 for computational methods. So this homework is going to be broken up into 7 parts, and they'll all be listed in the playlist that this video is going to be part of. And they'll be numbered 1 through 7. So let's get into it. So this is the assignment for homework 2. So this is part 1, video A, where we're going to numerically demonstrate the central limit theorem. Okay. So to demonstrate the central limit theorem, first we have to know what the central limit theorem is. So the central limit theorem is a theorem that establishes that if you have independent random variables and you take all these random variables, take their averages, then their averages will tend toward a normal distribution, even if the original variables are not normally distributed. So, what is a normal distribution? So, let's talk about what a normal distribution is first. So, normal distribution is something like this, where it's a distribution of values where it's basically a symmetrical distribution that has unique properties such as within specific standard deviations, you have a relatively known percentage of your probability of your variables. So what I mean by that is around the mean, so around the average, plus or minus 1 standard deviation away from the average, you'll get like 68% of the values. And around 2, it's like 95%, and around 3, so 3 standard deviations away in either direction, you'll get about 99% of the values. So all standard deviations follow this. And here's a graph showing kind of what it looks like. So this first one, the blue line, shows a mean of 0. Sigma squared is variance. So variance is 0.2. So it's a symmetrical graph around the axes, and its standard deviations kind of blend. Well, all normal distributions lend to this particular shape, and they're a very unique distribution. So what we're gonna do here is we're going to demonstrate the central limit theorem by actually using our own random independent variable. And what we're going to use is we're going to use a uniform distribution, where kind of like a dice roll, where you can get any number 1 through 6. The probability, if you roll it say 100 times, probability will kind of be pretty even between the numbers 1 and 6. But if you then take the averages of those sets, say you roll it 10 times, say you roll 10 sets of 100 times, take the average of those 10 sets, you'll get a normal distribution. So let's get started. So the first thing we're going to need is we're going to need to import numpy. Now to show this, we're going to need to do something like how do we want to do this? So in essence, what we're going to do is we're going to create an array of random numbers. So we're going to use np.random.uniform. And here we're supposed to, and so using this function, it's going to give us random uniform numbers. let's say between -10 and 10. And let's give it a size of 20. So what this should do is it'll give us 20 random numbers between -10 and 10. So this is what we're going to use to create our uniform plot. So space down. First we're going to do n sets, and we'll do 10 sets. And so the number, and we'll do, let's do 100. So what this should do, okay. Okay, so now we have a lot of data. So it looks like what we did is we have 10 columns and about 100 rows, and that's about what we want. So let's assign this, just call it samples. All right, so now what we're going to do is we're going to create a histogram. So let's do counts bins equals histogram. No, that's not what we want. We want, okay, so histogram. Then we want to give it samples. Then we want to identify how many bins we want. So let's actually make that. Let's give this here. Let's do n bins. Let's do 20 bins. Run that. N bins. Okay. Okay. Now we need to actually bring in Plotly. So from Plotly subplots import make subplots. Put it in here. Okay, so now we have this. What we're going to do is we're going to take our counts and our bins that we made just then, and we're going to put it into this. And we're going to do that is we're going to add bar, I think. Let's see if that's the right syntax. Then we want to do bins counts. Is that right? No. Okay, so it was wrong. So do we have to put an underscore then? Oh. So what this will do is it'll put our bins from that we made at each number. That'll be on the X. Then each randomly generated number at each bin will be our counts, which are our Y. So that should work. Bingo. All right. So here's our histogram. And as you can see, it's pretty evenly distributed. Let's make this easier to see. Let's put more in. There we go. So as you create this histogram with uniform numbers, it'll be pretty evenly distributed. And the more numbers you give it, the more evenly distributed it will be. So that's a good example of that. You can see that, yeah, they're all pretty much even. Let's add another 0. Yeah, see, as we get more and more, it gets more and more even, more and more uniform. Okay, so this is the data we're going to use to demonstrate our central limit theorem, because this data right here is not normally distributed data. This is uniform. And if we were to plot that in a graph, it would just be a straight line, just kind of like this bar graph is here. So what we're going to do is we're going to take the averages of all this data, and that's going to be and we're going to take those averages and then plot them in a very similar way as we just plotted these. And we'll be able to see it that way. So let's do, sample average equals np dot mean. We want it to be the mean of the samples, comma, oh, see if that works. Okay. So we might have to specify how many x's, so x equals 1. Okay. And then what we're going to do is we're going to just copy and paste this. Just make it figure 2. I guess that doesn't have. Run that. Yep. Sample average. Bingo. So, as you can see by this histogram, actually, let's make this a little bit more easier to see by giving some more bins. Let's do 50. As you can see, it kind of roughly has that shape where it's heading towards 0, which 0 is the mean of this data, which is kind of similar to something like this red normal distribution, where it's kind of, it's central, it's pretty symmetrical, and it has that kind of bell curve shape. So let's reduce that and see if we get a better picture. Yeah. So you see, and because we're randomly generating this data every time I run this cell, the more times we do it, every time we do it, it'll show a different graph. So this is an example of the central limit theorem, and that will conclude part 1 of the 7-part homework. Join us in part 2, where we will just derive the the expression for the entropy of a probability distribution. So I hope to see you guys there. Thank you.